Greetings, aspiring scientists. Welcome to my video today on collision theory. This will be topic 2.2.2 in the reactivity section of the IB Chemistry SL curriculum. So I hope you're doing well. Let's get started and go to my slides. So here we are, 2.2.2. I'll also try to do the next few chapters in today's video as well. But mostly they are related to collision theory. So we'll start with a bit of review, I think, the kinetic molecular theory of gases. If you've already studied ideal gases back in structure, you should know about this, the ideal gas law and the idea of ideal gases as a model. So we learned this gas law, PV equals nRT, pressure times volume equals number of moles times the gas constant R, 8.314 joule per Kelvin per mole, multiplied by temperature in Kelvin. So this generally holds true if a gas is ideal. And what are the properties of an ideal gas? What makes something more ideal than something else? Recall everything you learned about ideal gases, so we will have to remember what are the properties of an ideal gas. Check definitions if needed. We will do that on the next slide. So first, gases are composed of very small particles that are spherical in nature, which are far apart from each other. Most of the volume in the container is empty space. I should mention they're far apart from each other most of the time. Collisions are still possible, okay? Second, these particles are moving in straight lines in any direction, so they're not curving around, but they can move in straight lines and bounce off things to change their direction. And they move in 3D space, in our 3D universe, so if there's an X, Y, Z axis, they can move in any of those directions. Third, these particles undergo elastic collisions. That means no energy is lost when they rebound or transfer it to a colliding particle. And no energy is lost when colliding with the walls of the container. So these particles apply no force of attraction or repulsion on each other. That kind of goes along with traveling in straight lines. They're not able to apply any force at a distance of attraction or repulsion. And then fifth, the kinetic energy of a gas is directly proportional to its temperature, absolute temperature in Kelvin. So if you double the Kelvin temperature, you should also double the kinetic energy. Okay. Now, this is a description of an ideal gas in standard conditions. And I think a real ideal gas does not actually exist. We have things that are kind of close. But we can ask what kind of gases approach this definition and which ones are farther away. But it's still a good model to think about, because if you can explain things for ideal gases, you can explain things for a lot of gases that happen to behave ideally at high temperatures and low pressures, right? That was another thing you probably should have learned. So today we'll get into collision theory. We were talking about rates of reaction in previous videos. So now we want to say, how do we control the reaction and what is the theory and the model behind any of the reasoning we have for why certain things affect rates. Okay, so for a chemical reaction to happen, some conditions must be met. The particles involved must make physical contact. They must come in close proximity of each other. This is known as a collision. And when we say close proximity, we mean really, really close. It's kind of hard to exactly define where an atom begins and ends because of electron clouds being just probability based. But they need to come so close together that their nuclei and electrons start to have very strong forces with each other. We would call it coming in contact. Second, the particles which collide must have the correct mutual orientations. So I have some good slides to explain exactly what that means coming soon, but basically it means that when there's a collision, this 3D object must be facing kind of this correct direction, and the thing that it hits must also be facing the correct direction for the collision to mean anything and have any consequences other than just a rebound. Okay, third, the colliding particles must have a required amount of kinetic energy to break, form, and rearrange the required chemical bonds. Okay, so we can have a collision, but if things are moving extremely slowly, there's just going to be a slight rebound and change of direction. If we want to have a chemical reaction, that means change in chemical bonds. We need them to kind of smash into each other, right? And have the bonds really be shaken, moved around, broken, reformed. So that's kind of a minimum required energy for that to happen. And by raising the average kinetic energy, the temperature, we can sort of, on average, increase the chances of this going well for our reactants. So number one is a very general thing, just the particles must come in contact. Number 2 and 3 are true for every reaction, but what is required is different for every reaction. So the correct orientations really depends on what the reactants are, and the required kinetic energy also depends on the reactants. Some of it could be really high, some of it, even if they collide at low speed, the reaction will go. Okay, what else can we say? I want to show you some models of this. So I think this will show you collisions based on kinetic energy. Okay, so on the left side, when I start this little simulation video, our particles are at 150K, so that's fairly low. And then more than double that, 365K, so we should see the right side particles moving a lot more. And then you can count the collisions. We also have the average speed in some units I don't know, but just arbitrary units. So when I start this, all right, you can see the collision counter is going much faster, and I'm going to increase it to the max, 1,348 Kelvin on the right. Collisions go way up. I will just show that again quickly. So when there's higher kinetic energy, higher average speed on the right, the collision counter goes up more. We can bring that up to the max to really push it and show the number of collisions increasing. Okay, so higher temperature, absolute temperature, and higher kinetic energy will lead to many more collisions. This is a 2D model, but very similar things will happen in 3D. All right, what about the orientation? Here's a little diagram to show this. If we have these two molecules, BA and CD, colliding together, if they collide in such a way that B hits C and A hits D at the same time, we'll get breaking of bonds and reforming in a very favorable way to get new products, BC and AD. This is a successful collision if the kinetic energy requirement is met. They have to smash into each other with enough force to break the BA and CD bonds and form the new bonds. If they're going too slowly, they'll probably just bounce off. All right, but if we have the orientation BA collides in the bottom here, B hits with D and A hits with C nearby, even if this goes at high kinetic energy, there's not likely to be any reaction because maybe B and D and A and C strongly repel each other in almost any case, so they won't form new bonds. So there's no reaction with that orientation. So you start to get the picture of things need to be moving fast, smashing into each other, and even then there's only a % chance that these things are actually oriented or facing the right way. So a lot of things have to go right. So I also have a little animation here to kind of simulate the orientation problem. I'll see if you can guess what's going on here as I play it a little bit. Okay, so did you see a couple reactions happen where things disappear? So what needed to happen? The small single orange ball needs to collide with the orange ball in a molecule of orange and gray. If that happens, they react and disappear. But you probably also saw a couple collisions there where orange balls, the single and the double collide, but there still wasn't any proper reaction. Why is that? Well, let me show now where the orientation cone exists. It's an angle on the orange part of the molecule where this must be where the single ball hits for a successful reaction to happen. We'll see if we can observe that. So there was an unsuccessful collision on the right. Unsuccessful, oh, there's a couple successful ones there. So if the orange ball hits inside that cone of reactivity, that's the right orientation for this collision, then we can have a successful reaction. Now I think what I'll do is expand this cone to make this reaction more likely to succeed. I'll bring it up to like 90, I'll bring it down first, sorry. So that should really decrease the rate of successful collisions because it's less likely now that we're gonna collide right in that cone. There's one success, but overall quite a lot of failures. If we increase the speed though, increase the temperature, it should bring things back up a little bit. There's just more collisions now, so more chances of success. If we let that go a little bit longer and actually counted it, you could see it pretty clearly, I think. A couple failures. Now we'll try to just get this going really fast reaction where we have a good orientation, chance, and particle speed. There should be a lot of collisions happening now and a lot of successes. Yeah, there's kind of a bad luck zone there, but now we had a bunch in a row. And everything's just chance-based. So you can see in my simulation here, some of those stats. So overall, it's a combination of the number of collisions and the orientation allowing a successful collision to happen, right? Okay, thermochemistry. Reaction profile, this is a bit of review from the enthalpy section. So I did introduce this energy profile where we can have exothermic or endothermic reactions where the products are either lower or higher than the reactants on this potential energy scale. But I think I also mentioned in those videos that there's always going to be an activation energy, which we label with EA. It's kind of this first hump that the energy profile must overcome before it goes to products. It exists in both exothermic and endothermic types. Now, when we talk about the energy required for a successful collision, what we're really talking about is this activation energy. Okay, we need a certain amount of energy overcome, even though this doesn't represent anything to do with the difference between the reactants and products, that delta H. The EA, activation energy, is still required to be overcome for a successful reaction. Okay. Now, when the molecules collide, they must have the correct orientation and enough kinetic energy to overcome the activation energy and form a transition state. So a transition state is on the very top of this profile. It's sort of the highest point that your reaction pathway will ever be at. It's kind of a very unstable thing that involves multiple bonds being formed and broken at the same time, all connected onto your target molecule, which is why it's very unstable. We'll get into that a little bit in the future, but just for now, so you're aware of what this terminology means. So let's review. For a chemical reaction to happen, we need particles involved to make physical contact. They must come within close proximity of each other, making a collision. Next, the particles which collide must have the correct mutual orientations, the way that they are facing each other in 3D space. The colliding particles must have a required amount of kinetic energy to break, form, and rearrange the required chemical bonds. We can now apply the word activation energy to that minimum required kinetic energy. All right, so that's everything for 2.2.2. So I will talk about 2.2.3 as well today. This is factors affecting reaction rates. So we'll just apply everything we just learned and say, how do we control that in the laboratory or in any specific situation? So we'll consider 4 main factors that can affect the rate of reaction, and our explanation for why these affect rate, which you also need to be able to explain, they're based on the collision theory that we just looked at. Now I know we looked at the collision theory and kinetic molecular theory and the ideal gas law kind of as applying all to gases, right? But a lot of other materials, solids and liquids, will have either some connection to this theory or some approximation with it where the ideas behind it still apply, okay? So number 1, increasing concentration of the reactants involved. I should say increasing or decreasing really, but just changing the concentration in any way. Okay. So, just adding more concentration, more particles in a certain space should increase the rate, and decreasing it should decrease the rate. Second, adding a catalyst to the reaction medium. Now, a catalyst I think is one of the last things that we'll talk about in this topic, but just for now, try to memorize it or be aware of it, that adding this thing called a catalyst can change the rate of reaction. Third, increasing the temperature of the reaction medium. Again, we're just saying affect rate, so I should also say or decreasing. So as I showed in some of my simulation videos, increasing the speed not only has more collisions, but things are going faster, so when they collide, they're going to have more combined kinetic energy on average. So those are 2 very good things for affecting the reaction rate. Fourth then, decreasing solid particle size or phase boundary size. In other words, increasing surface area for collisions. Okay, so you can imagine if we're trying to get a gas or liquid to react with a solid that maybe we drop in, there's going to be a surface area where collisions can happen. They can't really happen in the center of that chunk of solid, right? And solid reactions I think are quite rare or slow, so we really won't focus on those. So let's go through these. So higher concentration particles per unit volume will lead to more collisions. Conversely, lower concentration will lead to lower number of collisions. This is why reactions slow down over time. You can generally take that as a rule. If you have some set number of reactants and you start a reaction and get them going, the rate of that reaction will be fastest at the start and then will slow down. As the reactants start to disappear, their concentration goes down. So I have a little simulation video again here. So if I just have 2 containers, one of them has 50 particles, one has 15, and a little collision counter, counting collisions per second basically, there's a lot more collisions happening when there's more particles. There's just more chance of hitting something else on the way through its path. And that's basically all there is to it. More particles, more chances to hit something. Again, this is a 2D model, but very similar things and probably even greater effects in 3D. What about pressure? Well, pressure essentially has the same effect as concentration. If you remember the ideal gas law, PV equals nRT, and rearrange that for pressure. So pressure equals number of particles times gas constant times absolute temperature divided by volume. So there's essentially 3 variables in there that you could change to change pressure. You can add more particles like we just saw in a previous video. You could increase the temperature, or you can decrease the volume. So what I want to show in this slide's video is just taking the same container with the same number of particles, 30, decrease that volume essentially by half. This is a 2-dimensional thing again, so we have area instead of volume, but the idea for 3D things would be very similar. So if I play this, same number of particles, but the right side container has higher pressure because the volume has been reduced. Area in this case, surface area, but you can also apply it to the idea of volume. And it looks like
reduced.
This surface area creates way more collisions per second, right? It's not like double really, it's more like 4 times. It's probably because we've decreased 2 sides of this square, right? The length and the width. You can imagine if it was a cube in 3D, this would probably be even higher because you would decrease the height as well. So pressure has the same effects as concentration basically. If you increase pressure, increase rate. Decrease pressure, decrease rate. But this really only applies when gases are involved. If you look at the bottom point here, so pressure is variable in gases, but not very much inside solids and liquids. Therefore, this parameter is only considered for gases. It can still be considered if you have a gas reacting with a solid or a liquid like at the surface. But if you have like liquid on a solid, we won't be considering pressure, for example. So some vocabulary that goes along with what we're going to talk about next. Phase. This generally refers to the physical state of a medium. You would have learned this back in like topic 1.1, I think. States of matter, solid, liquid, and gas. Those are also known as phases, but we'll also consider separate layers within a state now. For example, you can have 2 liquid phases if you mix water and oil together. They have a boundary where they don't mix, and there's a certain surface area that goes along with that will dictate rates of reaction where you're trying to mix, things in the water and the oil. But these can exist for gases and solids as well, basically anything you can imagine, any combination. So heterogeneous mixture, this was also from early on in the mixtures section of this course. Hopefully you remember that a heterogeneous mixture has the molecules in 2 different phases. They can only react at the surface between the phases. So before we described this as like not being evenly distributed and having regions of different density, now we can describe it a little bit as different phases, right? If you imagine like a chocolate chip cookie, for example, there's the phase of the butter and egg and batter, the cookie part, and then chocolate chips. Those are kind of different phases within the chocolate chip cookie solid, and that is a heterogeneous mixture, therefore. So heterogeneous mixtures, where we're trying to react things in different parts of that mixture, often have a slower rate. For that reason, there's minimal surface area where there can be interactions. Compare that with a homogeneous mixture, though. In this mixture, there's only one phase that has essentially equal concentration spread throughout. This will often have faster rate for that reason. We're not dealing with a surface area at a phase boundary in that case. We're dealing with just a set concentration, and inside that volume, all the particles can react. Now, solid surface area. Here's an important idea. If we're trying to get particles to react, usually this will be, as I said, liquid or solid particles, these blue ones on the outside, to react with a solid. They can only react with the outside layers, not the central atoms inside a solid crystal, right? So we can have these particles colliding and reacting with the outside. If you have a big chunk, that reaction rate is going to be fairly slow. But as you make particles smaller, maybe chop up this cube, the same volume into 4 smaller cubes, now we have way more surface area available for the outer particles to collide with, so this reaction rate is going to go much faster. So smaller particles with the same total volume can have more collisions with the surroundings. I'm sure there are mathematical formula that can prove this, but hopefully this picture can as well. Again, this is kind of 2D. You can imagine particles collide with the front, back, top, bottom of these cubes. More collisions will be possible with smaller particles. Now, the reaction rate depends on the surface area between the phases that are available for collisions. So you can imagine a real thing now, a chunk of coal that maybe you're going to burn in a reactor or an oven or something, engine for fuel. If you just have a big chunk of coal, it's not going to burn as quickly. The rate of combustion will not be as high. If you have powdered coal, way more surface area on those particles available for collision with oxygen. So a large solid piece of coal will combust much more slowly than a finely powdered coal. And this is true for pretty much any solid that can do a reaction. When it's powdered, that's the most quickest reaction rate you will accomplish. The surface area and the frequency of possible collisions is greatly increased for fine powders. Now, a similar idea to that, what if we're trying to react a gas with a liquid? We can bubble it through. This creates a phase difference. This is an analogous situation to the coal reacting with a gas, but the rate of a gas reacting with a liquid can be increased by bubbling it through a solution rather than letting it float on top, okay? If we want a liquid to react with a gas, we could just put a bucket of this liquid in a room with the gas, right? That's going to be extremely slow. If we want a quick reaction, use a bubbler and we'll get bubbles passing through. This will create much more surface area. Now, there's two bubblers here though. One of them creates sort of large, infrequent bubbles. This is better than just letting the gas rest on the top, but the one on the right creates fine, many bubbles. Even if these two have the same flow rate, the smaller bubbles will create more surface area, more places of possible collisions between the gas and the liquid. So faster rate for smaller, more frequent bubbles. All right, so some notes about concentration and temperature. Things like concentration, pressure, and surface area sort of belong to the same family. They just allow more collisions to take place between your reactants. The frequency of total collisions are connected with concentration, pressure, and surface area. Compare that with temperature though. Concentration, pressure, and surface area don't have any effect on the proportion of successful collisions. So when a collision happens, there's going to be some percent chance, like 25%, 60%, 80%, whatever it is, for that to be successful. So concentration, pressure, and surface area do not affect that percent chance at all. They just say more collisions possible, but not the chance of success for a collision. Temperature, though, is the main thing that will increase kinetic energy and increase the proportion of successful collisions, both of them at the same time, because everything moving faster will overcome their activation energy, but everything moving faster will also increase the number of collisions. All right, so for this reason, temperature is the most effective way to increase rate. It increases, if you increase temperature, you increase two very important things: proportion of successful collisions and number of total collisions. But raising the temperature requires energy, which a lot of the other things don't really require, right? Concentration, you can just add some more stuff into the space. Pressure maybe requires energy to pressurize things, so that's true. But increasing surface area of solids maybe requires a bit of energy to like shave things into a powder, but temperature is the main thing that's going to require a lot of energy if you're trying to increase the temperature of your whole reaction vessel every time you do the reaction. It may not be economically viable to do things at super high temperature all the time. So I only have one practice today, this one here. So here we have a reaction. Hydrogen peroxide, H2O2, goes to water, H2O, and O2 gas. Here's a graph similar to those from my previous video where we have some products being formed. We have a steep increase at the start as the rate is high. You could draw a tangent line there. That initial rate is very high. And over time, it levels off until the reaction is finished, about halfway through that time there. So in this graph of oxygen produced in the decomposition of H2O2, draw three new curves to show how the reaction would proceed if there were some different things. So first, increase initial concentration of reactants in the same volume as the original reaction. Second, lowered the temperature. And third, increased atmospheric pressure. And this type of question is very common on IB exams when it comes to understanding reaction rates and collision theory and things that affect rates. That's why I chose this as today's question. So let's do number one. If we increase the initial concentration of reactants while keeping the volume the same as this original case, what would the graph look like? Well, you first have to ask, will the rate, and especially the initial rate at the start, be affected? We have more particles inside the same volume, increased concentration. What happens to rate? Rate increases. So the initial rate will also be faster. Something like this. Steeper slope, steeper tangent line. And of course, it's going to curve to the right. It's going to slow down and stop. But what can we say about how it finishes? We don't know exactly how much this concentration was increased, but we know if there's more starting materials, right? We know C equals N over V. If concentration was increased and volume was the same, and concentration is proportional to number of moles, number of particles, it must be true that there are more reactant particles in this number one. And if there's more reactant particles, there's only one reactant in this reaction, right? It will produce more products. We'll get a higher number of moles of products. That means that this volume, which is also proportional to number of particles, will increase. So it needs to finish at a higher spot. Okay, so this volume needs to finish at a higher volume than it was previously. It needs to level off at a higher position. Something like that. Okay, faster rate at the start, steeper slope, and higher finishing volume position. More reactants, more products, more volume of gas. So that was number one. What about number two? Lowered temperature. In this case, we haven't done anything at all with concentration or number of moles or pressure. Lower temperature though, how does that affect rate, and especially initial rate? It will have lower rate overall. Lower frequency of collisions and lower kinetic energy means we're not meeting the activation energy requirements. So maybe I'll change color, blue. So number two, lower temperature, lower initial rate, lower rate overall. But where will we finish? We'll finish and level off at the same place as originally because we have the same number of reactants. That means we can produce the same amount of products and essentially the same volume. I might have been able to draw a slightly better looking curve than that, but the point is that the initial rate is lower. Tangent line would be more flat. And when it finishes and levels off, that number of products is the same as it was before because we have the same amount of reactants. That's number two. All right, number three might be the most difficult to consider because you have to really consider what this affects and everything we talked about and what different phases might be happening. So increased atmospheric pressure. Does increased atmospheric pressure affect a reaction of H2O2 aqueous? And the answer is no. It does not affect that reaction. It does not affect that rate even. Does it affect our products in any way though? Well, if we're going to have O2 being released and then filling a container that is presumably at atmospheric pressure, and we increase that atmospheric pressure, pressure is inversely proportional to volume. So that means whatever volume we measure will be lower than the original case. So we might have, I'll use green here, might have our reaction finishing here with increased pressure. But the rate should essentially be the same as it was originally, especially the initial rate there. It's just when the gas escapes and we actually measure its volume, it can't have as much volume as before because we have higher pressure now surrounding it. Okay, now if this was just gases reacting and you increase the pressure, that will actually increase the rate. Gas rate depends on pressure, unlike aqueous solutions or liquids. So just be aware of that. These questions can get fairly tricky sometimes. So that's what I would say about how you can answer this question and draw these graphs. Very important to understand and get a few points on your exams. So I think that's all I have for today. Next time we'll talk about activation energy and catalysts and finish up the reaction rates section of the syllabus and my videos. So that's all. Thanks for listening. Good luck. See you next time.